Things like this are different because you go, boy, it's a short week. Then you realize how much you have to do. Crap, it's a short week. I would rather. All right, now we're going to embark on discussing in some detail each and every, at least almost each and every drug delivery system, and try at least give a shout out to everything, concentrate on the ones of greatest importance to start with. The drug delivery systems that we'll focus a significant amount of our time on are solid oral drug delivery systems, tablets and capsules, and the like. Preparatory to talking about them is this particular section on micromoretics. This is one of those terms that spelling it can be a challenge. Sometimes I put the I's and E's in the wrong place. But tablets and capsules tend to be made out of the ingredients that go into their processing machineries are powders. So it's the study of those that this entails. So properties of powders. We can manipulate these properties to give us the features necessary in order to produce whatever drug delivery system we desire. The processing equipment for a tablet and a capsule are in some ways a little bit alike, but they're pretty different. And the properties for a tablet are a little more rigid than they are for a capsule. A capsule isn't just powder poured into a shell, actually makes sort of a soft tablet mostly that goes in there. And that's easier to do than to compress powder into a solid that will stay the form of a tablet. So powder properties, something to help make the dosage form and give therapy at optimum values. So we put it into individual drug delivery systems so that the patient can self-administer, make it easier to measure out a dose. Micromoretics looks at these properties from these standpoints. Particle size and particle distribution can also include shape in there. Although for the most part, when we do these types of evaluations of powders, we tend to approximate in our estimation that the particles are roughly spherical in shape, which is not an unreasonable idea because you can get maximum content and minimum exposure to the environment in a sphere. All you have to do is look at a drop that comes out, drops of water, drops of rain, etc. Those are roughly spheres. What makes them elongate into more tear-like qualities is the effect of gravity as they fall. Also, part of the properties we would look at and become important in terms of putting a formulation together for a tablet or a capsule are things called porosity, void, and bulk volume. These are somewhat interrelated. The density of the material comes into play when we're compressing something. And there's two densities. The true density, which is what we talked about in Chapter 5 in calculations, that deals with the true density of something. But the apparent density is when it's a pure powder and we're processing it, its density properties are a little different than when it's a solid chunk of something, as well as its bulkiness. And all of these go into the size and the type of processing equipment that can be used. So micromoretics, by definition, is the science of small particles. And by changing the properties of these particles and their relationship, then we can affect the outcome when we're putting things together. It's one thing to measure the properties of an individual substance, but we also have to take into account the properties of different powdered substances as we're mixing them together. And if they're very, very different, then how they combine may not be what we desire. So in some instances, the micromeretic properties of different powders that we put together may need to be more similar than more different. So particle size. Particle size is usually estimated as an average. It's not impossible, but nearly impossible to have uniform particle size for an ingredient. And if you could do that, it would be horrendously expensive. So we look at a particle size range, sort of like a distribution. And then we're looking at the average or the mean. Because you're going to have many different sizes that are there. So the greater, you might want a certain particle size, but you may also want that particle size to be either widely distributed or very small distribution. Think of it as a statistical type of problem. Your standard distribution curve, you have your mean in the middle. Well, we can look at particle sizes that same way. So we can have particle sizes in which this is the distribution of particle sizes. That will be the mean, this is its distribution, so low values and high values. Or it could be something like this. So the particle size distribution is much wider, which means we have a lot of smaller particles and a lot of larger particles that we don't have in this case. That's supposed to be approximately equal, and it's not. These two might have the same mean particle size, or average particle size, but they would not have these same properties because of these very large particles out here and very small particles out here that don't exist up here. So it's not just particle size, but it's particle size distribution that go together for importance. So importance of micromeritics in pharmacy. So size and size range are very important for the reasons that are listed here. Because the surface area that's around is potentially reactive. How the particles pack together matter because how they mix with other particles would make a difference. The flow properties of particles. Sand flows pretty well because its particles are roughly spherical and pretty uniform for fairly small particle size distribution in most sand. Most pharmaceutical powders aren't that narrow. The particle size of the drug, once it's incorporated into the drug delivery system, can also affect how the drug is released. The smaller the particles of drug that are incorporated and compressed into a tablet or included in a capsule, it may affect its ability to go into solution and be dissolved and released. If we want it to be delayed, then we can play with the particle size and the distribution to delay that. So smaller particles tend to dissolve quicker. That's not universally true for all drugs. So there are some where larger particles actually dissolve better, interestingly enough. But as a general physical chemical process, faster dissolution that comes from smaller particles. Accurate determination of pore size for filters depends on the particles. Antigens may be coated on adsorbent particles, so these are some of the importance, and you can read those as well as I can. Properties in suspensions and emulsions are affected by the particle size of the ingredients that we put in there. So a powder sample is typically characterized by three things: the shape of the particles, size of the particles, and the size of distribution. As I said, for the most part, we tend to think of the shape as spherical. So they can sort of tumble over each other. Although there are certain particles, if they're made of large crystals, may be a little more cubic in nature. But thinking of them as spheres for most of the calculations and most of our estimations tends to actually work out pretty well. If they're not spherical, if they're significantly different from being spherical, then characterizing the particle can be very difficult. And even though we think of them as spherical, they're not perfect spheres. But that's an approximation that we make. Said if all the particles had the same diameter, powder sample would be a monodispersed system, but most of them are not that way, so those are considered polydispersed systems. This means they're made up of ground parrots. Nothing. Poly. Which reminds me of a really stupid joke. What does a 500-pound parrot say? Polly want a cracker. Now. Anyway. I said it was really stupid. So, and I just said this, most systems that we deal with, even if they're approximately spherical, are polydispersed. Because to get something that's monodispersed would be extremely difficult and very expensive. So that's why we estimate the average particle size. There'll be some bigger, there'll be some smaller. This will be true of each and every ingredient, because they would all tend to come as solids or semi-solids. And how they mix together can be different. So experimentation would be necessary. What happens in a formulation scientist is they'll gather some raw materials of maybe different types of different particle sizes together and use some reduced size production equipment to see which ones mix the best or most efficiently or the quickest or something of that nature. It's called a pilot plant. It has nothing to do with flying. It's just, okay, it's sort of a smaller scale testing equipment before we go up into the big scale. So particles are non-uniform in shape, although we generally assume they're spherical. So these actually look pretty good for the most part, though we see some chunks of material that are in here. And we also see a range of sizes. So here's a small one next to a fairly large one, but most of them are somewhere in between those two. So that's where the average would probably be. So like mixing rocks and sand in a jar, if you want to get the maximum, you put the rocks in first, the biggest ones in first, and then you put the sand in. So the sand fills in the cracks between the rocks. Same type of thing for this. The big chunks take up some room, but then there are spaces between where the smaller ones migrate to. right, so average particle size calculated in this fashion. There are pieces of equipment that measure these directly. In the old days, you actually took a portion of the powder and put it on a slide and counted the particles of various sizes. The microscope had a scale on it so you could judge the size of each of the particles and plug it into an equation of this fashion. This is the one from Edmondson. Get the average particle size. There are equipment that now have a way where you take the powder and pass it across a surface that has some type of light beam across, and as that beam gets broken, it can judge the size of measure the size of the particles and do the calculation in that fashion. So these are what the pieces of the equation mean. I'm not going to ask you to do this calculation. This is just where that mean particle size comes from. So there's a lot that goes into it. So the number of particles in a certain size range, diameter of those particles. If the P is equal to 1, then that means length. P is equal to 2, surface area. P is equal to 3, the volume. So, as far as learning anything here, I don't expect you to memorize or even want you to memorize this, but this is where the components of this particular equation come in. All right, so when the number of weight of particles lying within a certain size range plotted against a size range or mean particle size, a graph is obtained, which is what I sort of drew up there to start with. So in this case, this is volume. It could just as well have been diameter. It would look similar, but this is volume versus particle size. So the histogram, or the number in each of those particular size ranges. So there's a distribution. There's some smaller ones down here, larger ones up here. So the average, the mean, would be somewhere in the center. This blue line is a cumulative distribution, so that's why it continually goes up, because you're adding all of the numbers together. So from the smallest to the largest. And then your piece of equipment would be measuring each of these histograms, and that's the way the data would come out. Things that are affected by particle size. Dissolution rate. And it tends to be the smaller the particles, the faster dissolution, because your surface area is greater the smaller the particles. So if the surface area for your drug is greater, its chances of interacting with the dissolution media, or the media that it's in, the stomach contents, GI tract contents, are increased. Now, conversely, if your particle size is too small, then the free energy of the surface of the really small particles will tend to attract each other rather than the media. So that could lead to an issue. And for some drugs, that's why larger particles actually dissolve faster than smaller particles, because of the free energy interactions. We want our particles to be small enough to dissolve, but not so small that they interact with each other. We want them to disperse. If they clump together, and we'll talk about aggregation and flocculation when we talk about dispersed systems. If they cling to each other, then that makes them less likely to dissolve, less likely to flow properly, less likely to have the properties that we need. So there's a balancing point. Small particles to a certain extent are good, but they can be too small. Distribution. In a powder mixture, we want them to distribute evenly. If you're trying to mix boulders and sand, there will be sections of it where it's only going to be boulder and only going to be sand. So we would want our powders to be approximately in the same orders of magnitude of particle sizes so that we can get a fairly even mixture of it. It's not a problem with solutions, which theoretically instantaneously mix, but with solids. It's also an issue, we'll probably bring this up at a later point in time, where when you're mixing, anybody that's made a cake from scratch and you have to put in the powder and the baking soda and the salt and everything, you mix it for a prescribed period of time. Did you ever wonder why it says mix for 10 minutes or 5 minutes or 15 or whatever? No, but you're going to tell us. Okay, yes, I will tell you. You can actually mix too long. You may not think of that when you're getting ready to paint something and you have to stir up the paint. You say, well, I'm going to stir the paint for a while, and if I can't really stir that too long. And that's kind of a liquid system, so that's all right. But when you're mixing powders, if you mix them too long, what happens is you start unmixing. Is the particles from the separate components start separating instead of dispersing. So there will be part of, again, that pharmaceutical scientist in a pilot plant will be looking at the optimum time to get a nice even dispersion before they start unmixing. And they'll do that by mixing a variety of times and taking a sample and seeing what the distribution of products is throughout that. So mixing time is critical. Mix it just long enough to get a nice even dispersion, but not so long that you unmix it. You could conceivably do that in a mortar and pestle also. So if 10 minutes is good, 20 minutes is better, isn't necessarily true. That's just like, okay, well, if one tablet will stave off a disease, then 2 will cure it, right? No. 1 is good, 2 is better. Doesn't work that way with pharmaceuticals either. Don't do that. Particles for inhalation need to be in this kind of particle size range. And if we expect them to stay there, they need to be closer to about 2 micrometers. Also, when you're making a semi-solid, an ointment, a cream, a gel, something of that nature, you're going to incorporate powdered drug. Someone's going to put it on a rash or a burn. You want to make certain that your drug is dissolved or dispersed nicely throughout that product. And if you want an idea of what I'm talking about, take some Vaseline, some petrolatum, and mix some sand with it. Just kind of mix it up as much as you can, kind of disperse the sand, and then take that and spread that on your skin. It's like spreading sandpaper. That would hurt. If you don't disperse your drug throughout your semi-solid, it would just be like sand in petrolatum. It would be gritty. It would be a really bad feel. So pharmaceutical feel, grittiness is something you don't want to have. When I'm evaluating your products that you will compound, especially next semester, get into semi-solids, one of the things I'm going to do is I'm going to take a sample of your product and rub it between my fingers to see if it's gritty. And if it is, then your grade isn't. Gets cut some. So don't try to go so fast that you don't do it right, because you're going to have to do this for a patient at some juncture. Determine the particle size. And I'm going to start off next class with a demonstration of this. I thought I'd talk about it first and then bring in the equipment to demonstrate it. Is sieving. You have a series of screens with various holes in them. Put a sample of powder on the top of it, put it on a shaker, turn it on for 5 minutes, and let it shake through. And then we would weigh out how much powder got onto each shaker and based upon the screens before and the screens after, you can get a particle size distribution fundamentally manually. Microscopy, that sample, you would put it on a special microscope that had a size grid on it, so you could count the number of particles in each size range and get that distribution profile. Sedimentation rate, can put your powder in a liquid into which it doesn't dissolve, so it might be a water-soluble powder dispersed into an oil, so that would separate them so that you could count. It's sometimes necessary for some of the pieces of equipment to do that. And this uses Stokes' law, which we will talk about a little later. Light energy diffraction, light scattering, so some automated instruments might be able to use the powder directly, might have to disperse it in some type of liquid medium. So to characterize it, I have a sieve shaker that looks something like this. These are the sieves. Ones we have are made out of brass as well as the screens on the inside. So you would just take them, put the powder in the top, clamp it all down, and turn it on for a period of time, and again that period is 5 minutes. So the larger the sieve opening, the larger the sieve number, the smaller the sieve opening. So a number 200 sieve has smaller openings than a number 40. Classification according to USP is from very coarse to very fine. So this is the description of a sieve, and these are sort of the standard sieves that you would look at. So a number 20, number 40, so you can see the openings get smaller as the number gets bigger. So in a number 20 sieve, you can easily see the openings between the wires. So about 850 microns down to 74 microns. So you put your powder on top of this, bigger down to smaller. As it shakes, the powder just kind of shakes through, and then you would evaluate how much is laying on each one. So what would be laying on a number 200 sieve will be particles that were smaller than 125, but bigger than 75. At the very bottom, if this is the last sieve that you have, at the very bottom is a tray. So anything smaller than 74 would simply get caught in the very bottom, and you would evaluate that too. So USP descriptive terms. If all the particles pass through a number 8 sieve, but no more than 20% pass through a number 60 sieve, these are considered very coarse. Coarse, all through a 20, no more than 40% through a 60. Moderately coarse, all through a 40, no more than 20% through an 80. Fine, all particles pass through a 60, but no more than 40% pass through a 100. Very fine, all pass through a number 80 sieve. As I said, I'm going to bring in our sieve shaker, and we'll do a little demonstration at the start of next pharmaceuticals class. So the other properties we talked about in terms of micromuretics: porosity, void, and bulk. And these become important in terms of processing and processing equipment, storage of raw materials, that type of thing. Also influence how particles flow. So flow affects the choice of processing equipment, type, size, features, etc. The size of drug delivery system we might be able to make, among others. Packing, size of the final drug delivery system itself. Choice of components for preparation. What size and or shapes of punches and dies that we might use. And we'll look at some various ones when we talk about tableting, as well as various and sundry capsule sizes. For human pharmaceuticals, how many different capsule sizes do we typically have to choose from? Let's get a little ahead of ourselves, but just see what you know to start with. How many? Who thinks 2? About 3. Well, Taker. 4? A couple of people. 5? 6? 7? Nobody? 8? 9? 10? Who didn't put your hand up? That's most of you. More than 10? It's actually 8 standard sizes. 1, 2, 3, 4, and 5, of which, interestingly enough, 5 is the smallest. And 0, double 0, and triple 0, which those are the 3 largest, of which the more zeros, the bigger it is. So how much powder you can get into a capsule shell is determined by its properties. Bulk volume, volume occupied by a given mass of powder, probably before processing, but we'd also measure the formulation after it's processed. To determine it, you would take a device, something like this. It's a tap density tester. This is a graduated cylinder. You would fill it with the powder as it would come as a raw material, or after you've processed it, or whatever the source of it. You would just fill it up to a particular volume, say 100 or 80 or whatever it might be. Then you would turn it on. Then it taps. It moves up and down. It's kind of loud. So it moves up and down for a set period of time, usually think about 4 minutes. Then at the end of that, then you measure the volume. So what that's done is any void spaces that are in there, it allows the particles to sort of flow down and pack in. So the type of process that would happen when it's run through processing equipment. The void is the space between the particles or the air. I know sometimes in the middle of the night you're studying something, you think it's that space between your ears. It's not. So don't think that. You don't have a void up there. Some of the people in the building over here, I'm not quite so certain of, but they're teasing. Sorry. So the closer the packing, the smaller this value. So this is expressed as a decimal somewhere between 0 and 1. So a uniform sized particles would have a predictable void space. So this would be one with a more narrow particle size distribution. The wider the particle size distribution, the less predictable this void space would be. So the void is you take the bulk volume minus the true volume. The true volume is the space occupied by the powder, irrespective of any spaces between the powder. So this is more related to the volume you would expect to take it up as a solid, as if it were its true density involved. Obviously the intermolecular spaces we can't get rid of. So you'd estimate the mass divided by the true density. That's how you get that. Porosity is actually just that same number expressed as a percentage, because the other is a decimal between 0 and 1. The apparent density is lower than the true density because of the air or the void space. So you may have expected a certain packing of material based upon its true density, but because some air is incorporated into the system, then that's where the apparent density comes in. This changes with applied pressure, and of course, theoretically, the highest the apparent density can be is the true density, and that's if you had no void spaces. The reciprocal of the apparent density is the bulkiness. So the reciprocal of how much you compact it is how much room does it take up. So the units will be just the opposite of what we would expect for density. All right, so as an example, so here's a potential calculation that you might need to know how to do. So I'll run through an example. So a drug has a true density of 2 grams per cubic centimeter or milliliter, both equated. So 20 grams measures 16 mils in a graduated cylinder. The true volume would be, of 20 grams, would be 10 mils. So the void is the difference between that. So this 20 grams, based upon its true density, should just be 10 mils. But in a graduated cylinder, it takes up 16. So that means the void is the other 6. And how to calculate the void space is 0.375 or 37.5%, the porosity. So even though this drug has this density, it actually takes up more room than that when it's in its quote-unquote processing form. So its apparent density, instead of being 2 grams per mil, is 1.25 grams per mil because there's 20 grams in 16 mils. You say, well, what difference does that make? Well, it makes a lot of difference if when you're putting something in, you have a container, you need to put your drug in. If you're going to put in 20 grams, you need to allow for enough room for 16 mils, not just for 10. So the bulkiness is the inverse of that, of the apparent density, so 0.8 mils per gram. So picking the size of your processing equipment, your containers, your mixers, those types of things, you have to allow sufficient size to mix it in. If you're making a large sheet cake, you don't start mixing your ingredients in a cereal bowl because it's going to be too small and everything's not going to fit in there. Same thing pharmaceutically, you want to make certain your processing equipment is of sufficient size to accommodate all of your ingredients, and this is one way to be able to calculate that. So this would still be considered a little bit of a heavy powder. Other thing in processing equipment, especially a tablet press, is powder flow. The powders are roughly spherical. Anybody used to play with marbles? We used to play with marbles. You not do that anymore? Yeah, okay. Marbles are round. You had a handful of marbles and you dumped them onto the ground, they would pour out of your hand very nicely. You got a handful of little tiny Rubik's Cubes. Why you would have little tiny Rubik's Cubes, I don't know. It's the only example I could think of that was square. And poured those out. Those eventually would fall, but they would kind of clump together. They wouldn't pour very well. So flowability of powder in your instrumentation is essential to maintain a nice mixture. Otherwise, if your powder doesn't flow sufficiently, then in processing a powder into a tablet, it's going to unmix and some of your tablets will have too much drug. Some of them won't have enough, if any, drug. That's another of those things that I would put in that general pharmaceutical category of that's bad. Figure if I keep trying that joke, at some point someone might laugh. But I've been deluded before. That's okay. You're going to estimate the flow properties of a powder. So rather than let's throw it into a machine and see what happens to it, which would be one way to do it, you can actually look at the flow properties. So two indicators of flow are angle of repose and flow rate. Angle of repose is not the position that you settle into on the couch when you're watching a football game. At least not as it relates to powder. Although there are some similarities there. And flow rate. Basically, your angle of repose in that case has zero flow rate. That's it. So we're going to set up an instrument where we're going to let the powder come out and create a pile that we can measure in a variety of ways. Kind of makes intrinsic sense when we go through it. So the angle of repose, that's the maximum angle between the surface and the heap of powder and the horizontal plane. So we'll back up for a second. So if this is where the powder flowed to, this line down here, and we have a nice pile of powder, in this case this one's shaped sort of like a pyramid or something like that, it would be more like a part of an upside down cone because it's going to be three-dimensional. Then this angle between the sides and here, that's your angle of repose. All right, so there are good angles of repose and there are not so good angles of repose. So think of that, that's your angle of repose. It's an indicator of frictional and cohesive forces in the powder. So how the particles interact with each other creates that cone. So you'd measure that angle of repose, once you have put down a particular amount of powder. Now generally this is done onto some type of balance or weighing device. So after you've allowed a certain mass of material to flow, then you would measure the angle of repose. Powder is released to a funnel, you form a heap, particles will glide over the heap, and depending upon how much they interact with each other as opposed to how much they flow, the heap is taller or smaller. Now, what do you think? Is it better flow if the heap is taller or if the heap is shorter? A few people said shorter. Other people looked at me like, I'm not going to answer you. So those brave people that said shorter, would you believe they're correct or incorrect? Nothing. Everybody that thinks they're correct, don't raise your hand. Ooh, everybody. Good. Because that's right. So the ease with which a powder will flow in a set of conditions. Now, pressure, humidity, the equipment, the materials made of, all those types of things matter. So here's sort of a graphic representation. You've got a certain amount, you let it flow through a funnel, you get a heat, there's a surface here, so you would measure that angle of repose. So here, very fine sand, which has a really nice flow. Its angle of repose is 35 degrees. Coarse sand's 40 degrees. Angular petals 45. Better flow, not as good flow. The higher the pile, the more likely the particles are to stay with each other rather than flow over the material. And we don't want them to stick together, not to have good flow. So the smaller the angle, the better is the flow. So you could have answered my hypothetical question from a few minutes ago by looking ahead 2 or 3 slides. So here are some various and sundry readings. So 25 to 30 degrees, considered very free-flowing, as opposed to 45 to 55 degrees, it's considered cohesive. So we don't want the powder to be cohesive when it's intended to flow. So here's an instance where probably do need to understand / memorize, I guess, but definitely understand which of these is better as opposed to which is worse. Because I might give you a hypothetical situation of, here's these forms of this particular ingredient, and one of them has an angle of repose of 50 degrees, and another one has of 40, and one of 30. Which of these has the best flow? And there might be a couple other variables in there as well. So from that standpoint, you would need to be able to make that decision. One way you could do it without necessarily memorizing all these, typically wouldn't say, well, which one's free-flowing as opposed to fair-flowing. That's not what I'm talking about. But look for the smallest angle of repose, that's better flow. That's what I want you to know. The bigger the angle, the worse the flow. The smaller the angle, the better the flow. I might have the question with numbers in it, but you wouldn't necessarily have to know the definition of the numbers to know this, because it would be a comparative situation. See the difference? All right, so flow rate, instead of through a funnel, there's actually an orifice, so this is designed to look at how it would flow through machinery prior to putting it on the machinery. Powder is placed and released, so it might be a little slide that's opened or something. So in the other case where we're getting the angle of repose, it was a funnel, so it should flow pretty well through that. So here it may not flow as well. So the weight of the powder, how they're flowing, force per unit time, so this is a function of time. So what might happen is, this is what we would prefer to have happen, is however big the hole is, when we open it up, it flows through nice and freely. As opposed to funnel flow, where there's some powder that sticks around the edges, you got to think of this 3-dimensionally, so it blocks it off some, so the flow is restricted. Here, rather than just in the bottom part, it sticks all the way to the top. This is referred to as a rat hole. So it's stuck all the way into the top. One of the other issues with these two types of things is if we're trying to deliver, if we need all of our powder to move through that orifice to be processed, some of it's stuck up in the feed chamber and it's not going to get used. Then there's arching, which just creates, instead of sticking here and there's still an opening, here it creates a bubble and it's like, it's blocked off and nothing's coming out. So this is what we want. These are some bad things that can occur. To prevent that, we might need to add other excipients to the ingredients that would help the powder to flow over itself. If it were 2 pieces of metal in a car engine, you would put oil in it. So we would add the pharmaceutical equivalent of oil, if you will. We're not going to put oil in it, but it would be an ingredient that allows the particles to flow over themselves and over the processing equipment. These are called glidants. And I have 4 more slides real quick. Comminution. Comminution is a general term and the definition of reducing the particle size of aggregates or powder materials. Comminution is reduction in particle size. This is a term I expect you to know. Such as in a mortar and pestle. When you take a powder, you put it in a mortar and pestle and grind it, comminution is one of the things you might be trying to accomplish there. You have tablets you need to turn into a powder, that's comminution. Now the processes, which are defined next, methods of comminution. Trituration. Moving around in a mortar and pestle, that process is referred to as trituration. You may or may not be doing comminution with that. If it's a powder, you probably are. But you can use trituration to mix a couple of liquids also. So trituration can be comminution, but not always. Pulverization by intervention can actually add another ingredient, maybe a liquid, a solvent or something like that, which allows you to grind the particles with them. Levigation might be something more like a semi-solid, same idea. Particle size reduction, a small scale, mortar and pestle, does good for solids. Levigation, this is a semi-solid in which you might be incorporating a solid or a viscous liquid into an ointment or a cream base. Sometimes you might use a mortar and pestle, but more often you would use an ointment tile. And particle size reduction, large scale, mills and grinders would be used for that, where you would have rapidly moving either blades or rollers or some combination thereof to try to decrease the particle size. You can make them so small, but again, you can make them too small.